Imagine I show you a three-dimensional surface that looks like this. How would you project it down to 2 dimensions? Well, there's infinitely many two-dimensional projections that we can form. First of all, we can create linear or nonlinear projections of this surface. But even within the family of linear projections, those can vary quite a bit. I could, for example, look at that surface directly from top to bottom and project it onto a plane of sight. In that case, I will see a projection that looks like this. My three-dimensional surface defined by x, y, and z is now represented in a two-dimensional coordinate system defined by eta 1 and eta 2. But I could also tilt my head and look at that surface from behind. In this case, a projection onto a plane of sight might look like this. These two are qualitatively very different projections. If I zoom in on a particular region on the first projection, I will see a very structured grid of data points. But an analogous region on the second projection might look like this. You can see that we no longer get a structured grid of points. Moreover, there is an overlap between some data points. From the perspective of the variable which colors that projection, the projection becomes non-unique inside the overlapping region. These are just some of the topological considerations of low-dimensional data projections that we need to address when we build models based on those projections. One such model can be training a linear or nonlinear regression function called f to predict some quantity of interest, given a set of low-dimensional coordinates as arguments of that function. If we use this projection to train a regression model, querying the model later on gives a correct answer. At that particular point, the quantity of interest attained the red color. But if we use the projection with overlap to train a regression model, querying the model is prone to large errors. For example, at the point which lands within the overlapping region, it becomes ambiguous which color should be predicted. There's 3 pieces of the original three-dimensional surface that are projected right on top of each other. They correspond to brown, red, and yellow. So, what is the correct model prediction? Likely, the regression model will make large errors in predicting the right value of a quantity of interest in those problematic regions on a projection. Here I'm showing the absolute error map from predicting the color variable using a regression model. You can see that for a fully unique projection, we get very small errors everywhere. But high errors are located near the overlapping regions on the second projection. It would therefore be really great if we could assess the projection quality before we even start building models on top of it. Ideally, we would like to have a metric that correctly informs us that this projection is a good projection and that this projection is a poor projection. We could then attach a single quantitative value to each projection that would inform us how costly is building a model based on that projection. A good projection would then have a lower cost, and a poor projection would have a higher cost. It would also be great if we could have an iterative algorithm that finds a good projection on its own, without us having to test multiple scenarios. Our Python library PCAfold, developed by me and my colleagues, contains all of those tools. The user can pass their custom high-dimensional dataset through a series of modules. The first module, preprocess, contains functionalities that help alter the dataset itself. The most straightforward operation is data scaling, but many other helpful items are available, such as data sampling, kernel density weighting, outlier detection, or data clustering. Next, the preprocessed dataset can be passed to the reduction module to reduce data dimensionality. In the analysis module, we include numerous techniques for assessing the projection quality. For example, the user can compute the cost, which turns a projection topology into a single number. Reconstruction module contains classes that help build and train regression models, such as artificial neural networks and partition of unity networks. Finally, the fifth module, Utilities, presents novel algorithms that can help improve low-dimensional data projections in an automated way. This module gathers novel tools from across the four main modules. PCAfold software becomes particularly useful if the original data dimensionality is high and if the projection dimensionality exceeds 3D, at which case the manual analysis of a projection quality can become tedious. You can find out more in the PCAfold documentation. In the next videos, we're going to dive deeper into particular applications of PCAfold functionalities. See you then!